Alrighty, last section of this unit is on rational expressions. So when we're dealing with rational expressions, that word that we've seen quite a few times, rational, means it can be represented as a fraction, rational fractional. For objectives today, when we talk about rational expressions, since they can be written as fractions, we're going to have denominators to worry about. So oftentimes we'll try and look for numbers that have to be excluded or thrown out. Number 2 will be a biggie, being able to simplify these. Again, this whole unit is about simplifying. The third objective is working with different operations with rational expressions. And then 4 will be kind of like the grand finale, or maybe the most intense out of all of the objectives. So, then we'll talk about this little graphic that I have here. This is what I call in my classroom a math sin, meaning don't do it. I do have a stamp that says math sin, and I don't want to have to use it. So, let's jump right in to rational expressions. And if it is a rational expression, that means it can be represented as the quotient of two polynomials. Quotient, remember, refers to division. So an example of a rational expression could be something like this. X minus 2 over 4. It's an expression that's represented as a fraction, which is why it's rational. Or it could be something a little bit heavier, like x squared plus 1 over x squared plus 2x minus 3. That is a rational expression. It's two polynomials being divided. So notice, especially on this second one here, if I have variables in the denominator, that's a scary thing in the math world because I don't want the denominator to come out to 0. I cannot divide something by 0. 0 cannot go into a number. So anytime we have variables in the denominator, we will often talk about what x cannot be, or how do we avoid getting 0 in the denominator. So this first example, find all the numbers that must be excluded from the domain of each expression. The domain just means everything that x could represent. So like if it could be 2 or 5 or negative 0.3 or negative 100,000. So like on this first example, look at the denominator. I don't want that thing to come out to 0. So what would x be to make that come out to 0? Well, if you can't eyeball it and know, just set the denominator equal to 0 and let's solve it. So to solve this, if I want to cancel subtracting 2, I add 2 to both sides, and it gets x equals 2. Let's draw a slash through the equals because what that represents, that is the number I do not want x to be. Because if I put 2 in for x, I get 4 over 0. I cannot divide by 0. That's garbage. So x cannot be 2. That's what has to be excluded. Every other number is okay, but not 2. Next one. Again, let's focus on the denominator because that's where my issues are going to be. I don't want that to be 0, so let's set it equal to 0 and solve it. Well, if you want, you could add 1 over. And then to get rid of the square, I would square root. A square root and a square cancel. Now the square root of a number when I'm solving comes out to plus minus. Because if you think about it, 1 squared is 1 and negative 1 squared is also 1. So what this means is there's two numbers that make the bottom 0. I do not want x to be 1 and I do not want x to be negative 1. If I plug in either of those, I'm going to get 0 in the denominator. Next one. Let's set the bottom equal to 0 and solve. Now this one's a little bit harder to spot Notice there's 3 terms. What we just did last section when we had 3 terms, we factored it, we marked it. So let's see if we can break this apart and see what it's made up of. I want to multiply 1 times negative 18, and I want to add to 3. So what 2 numbers multiply to negative 18 but add to 3? Should be a positive 6 and a negative 3. So if we rewrite it, group, so I get x minus 3 and x plus 6. So now the last step is I want to finish solving this. So you just set each piece equal to 0 and solve. So if I add 3, here I would have to subtract 6. These are the 2 numbers I do not want. If I plug in either of these 2 numbers into the denominator, I'm going to get 0. So I don't want 3 and I don't want negative 6. All right, moving on. Simplifying rational expressions. Well, we're going to be using a heavy amount of factoring. So if you're still confused on factoring, I suggest either asking me questions on it or watching the factoring video again. So what we're going to do, let's focus on the top. What could I factor out of the top? What is the greatest common factor that can come out of both of those? Should be an x squared. So if I take the x squared out, from the x cubed, I would still have an x. Now x squared divided by an x squared, there's still a 1. There's still a 1 sitting there. It's not just empty space. On the bottom, I can't do anything. Now the beautiful thing, remember I told you there's multiplication here. Since there's multiplication, but there's also division, multiplying and dividing can cancel each other. Since these are both x plus 1s, they're gone. And I'm left with just x squared. Now, oftentimes with these, behind this answer, they will list the values of x that we couldn't have. Well, if I look at the beginning, what would have been the x that I would have thrown out if I set the bottom equal to 0 and solve? Oh no. Subtract 1. I would not want x to be negative 1. Sometimes you'll see that listed behind the answer. That just represents the values that would be thrown out. Okay, let's do the next one. So let's break apart the top. I want to multiply to 5 and add to 6. What 2 numbers multiply to 5 but add to 6? Should be a 1 and a 5. So after doing all the rewriting, here's what your top should have factored into, just to save time. Now on the bottom, this is the difference of squares. Remember where we talked about the perfect square and the perfect square? That was this rule that said if I had the perfect squares, it broke up into a plus b and a minus b. So the bottom's really easy to factor. It would be x and x, and I'd have a plus 5 and a minus 5. Now, since I have my division and I'm connected by multiplication, I can cancel the x plus 5s. They would divide out, and I'd be left with x plus 1 over x minus 5. Now, here's where you have to watch out for those darn math sins. Sometimes people go what I like to call cancel crazy, and they'll go, oh, look at x's are gone as well. That doesn't work because, yes, there's division, but there was no multiplication here. It was addition and subtraction. So I can't cancel those. If it would have been something like this, with multiplication, then I could cancel them. But if there's that darn addition or subtraction connecting them, it doesn't work that way. So I would have to leave it as x plus 1 over x minus 5. And if they listed the restricted values, or the values that I have to throw out, there's 2 of them. Because when I factored out the bottom, there was 2 things that would have made the bottom 0 before I canceled anything out. Both 5 and negative 5 would have made the bottom 0. Okay, moving on. If you can do what we just did, multiplying rational expressions is just as simple. Let's factor everything that can be factored. I can't do anything with the x minus 7. I can't do anything with the x minus 1. However, up top here, x squared minus 1, I can factor that. That's the difference of squares. They're both perfect squares. So x and x, 1 and 1, one of each sign. How would I factor the bottom? Because there is something you can do to the bottom. I can take a GCF out. I can take a 3 out. So I'd have an x minus 7. So now let's look, is there anything I can cancel? Can I cancel the x minus 7s? And you should say yes, because there's division and connected by multiplication, so yes, I can cancel them. Can I cancel the x minus 1s? You should say yes, because there's division and there's multiplication. So if I write what's left, I have x plus 1 over 3. If I wrote the restricted numbers, or the numbers that I would want to throw out from my domain, well, from this left guy, I would not want x to be 1. That would make it 0. And from the other guy, it's easy to see that I would not want x to be 7. 7 would have made that denominator 0. Okay, if you can do what we just did, dividing is also pretty simple. All you have to do to divide is we're going to end up multiplying by the reciprocal of the second expression. For example, before I even do this problem, if I had 8 divided by 1/2, mathematically that is the same thing as doing 8 times the reciprocal of the second. So it would come out to 16. So what we're going to do here is I'm going to write this guy down. But then instead of division, I'm going to change it to multiplication, and I'm going to do the reciprocal of the second expression. If you can get over that hurdle, now it's exactly like the last example we just did. Now it's a multiplication problem. So let's factor everything. So this top guy here, I'm going to mark it. So I want to multiply to -8. And I want to add to -2. Two numbers that multiply to -8 and add to -2 should be a -4 and a +2. So I would get and on the bottom, I want to factor x squared minus 9. That's the difference of squares. They're both perfect. So x and x, 3 and 3, one of each sign. Now I can't do anything with the other two guys, so I'm just going to bring them down. And now let's see if we can cancel anything. Can I cancel the x plus 3s? And you should say yes, because there's multiplication here. Can I cancel the x minus 4s? You should say yes, because there's multiplication. That would cancel the division. So it looks like I'm left with x plus 2 over x minus 3. And if I listed the restricted values, or the numbers that I would have to throw out, it looks like if we do the right one first, I would not want x to be 4. And if I'm looking at the left set, I don't want x to be 3, and I don't want it to be a negative 3. Those would make the left denominator 0. Probably the biggest pain in the butt with these simplifying ones is if you have to add and subtract. To add and subtract rational expressions, you have to have a common denominator. Kind of like what we dealt with when we were adding those fractions a couple of sections ago. So just to review, if I had 1/2 plus 3/5 and I wanted to add those together, I would need a common denominator. Well, the smallest number that 2 and 5 would go into is 10. So I'd have to give this guy a 5, and I'd have to give this guy a 2. So if I give the bottom a 5, it would become a 10. If I give the top a 5, it would become 5. The other guy, if I gave it a 2, it'd become 6 over 10. Then I can add them together and get 11 over 10. It's the same concept for rational expressions. So let's look here. This first guy. Here's the denominator. Here's the denominator. Now, good news. They are the same denominator. So I can actually go ahead and combine these right away. So here's my common denominator. And now let's combine them. I would have 5x plus 1. Now, be super careful. This always stumps my students. This subtraction has to apply to the entire polynomial behind it. So I would actually have minus 4x plus 2, because I'd have minus a negative. It has to go to both. And now let's combine like terms. So 5x minus 4x, I'd have x. 1 plus 2, I'd have 3. And then my denominator. And then the last step, I would want you to check, can you do any further simplifying? Well, the thing that stands out to me, let's factor the bottom because that is the difference of squares. They're both perfect squares. So x and x, 3 and 3, plus and minus. And now we'll make a decision. Will anything cancel? And you should say, yes, the x plus 3's will cancel. So what's still up top if they canceled? Well, there's a 1 up there. And then I'd still have x minus 3. There would be my answer. All right, let's look at one that's not quite so nice. Now this next one, notice they do not have the same denominator. So the easiest way that I would recommend getting the denominators to be the same, we're going to give the one what the other one has. So like this left one, I'm going to be multiplying it with an x plus 3, because that's what the right one had. The right one, I'm going to be giving it a 2x minus 3. Because that's what the left one has. It's kind of like what I did here. I gave the left one a 5, and I gave the right one a 2. It's the same concept. So, one thing to keep in mind though, if I give it to the bottom, I also give it to the top to keep things balanced. So, when I write this, hopefully you agree, this is going to be in the denominator. The denominator is going to have those two items. Minus, and then the other one. All right, so up top, this first set, I'm going to have to FOIL them together. So first times first would be x squared. Sorry, my hand keeps brushing the computer screen, which is why all these marks appear. And then outer times outer, so x times 2. And then inner times inner. and then last times last, 3 times 2. Now the other one, I don't have to FOIL, I just have to make sure I distribute. And now the whole purpose why I got a common denominator is so that I can write this as one fraction. So I'm going to write it as one fraction now, and I'm going to combine like terms. So I have my x squared. 2x plus 3x is 5x, but then 5x minus 8x would be a negative 3x. So I combined all the x's up top. And then I have 6 minus negative 12. 6 minus negative 12. So that would be 18. Okay, and the last thing that I would check for is, can we factor the top? Now notice, you might be asking yourself, why didn't you FOIL the bottom? I'll tell you, don't worry about FOILing the bottom. The reason why we leave it apart like this is on the chance that at the very end, we can get something to cancel out. So like this top part, I would look to see if I can factor it. So I'd want to multiply to 18 and add to negative 3. So what would do that? So we might say, oh, a negative 6 and a 3. Well, yes, those would add to negative 3, but they don't multiply to a positive 18. It turns out the top doesn't factor, it's prime. So I would be okay if you left the answer like this. You would not have to multiply the denominator together. If I wanted to know what would be the values we would throw out, well, from this left guy here, x could not be negative 3. On the right one, if you're not sure, let's set that equal to 0 and solve. I'd have to add 3 over, and then divide by 2. So for the right one, I don't want x to be 3/2. Both of those numbers would make the bottom 0. All right, let's try one more of these. I'm going to need to do a common denominator. Now, to make a little less work for yourself, before you start doing a common denominator, let's factor the denominators. So this right one, that's the difference of squares. They're both perfect squares. So x and x, 1 and 1, plus and minus. And the other guy, if we were to mark it, I'm going to multiply to negative 2 and add to 1. What two numbers do that? It would have to be a positive 2 and a negative 1. So the bottom would factor into x plus 2 and x minus 1. So now when I go to do the common denominator, it's a little less work because I can see the red set, the only thing it doesn't have that the blue set has, it needs an x plus 1. And the blue set, the only thing it's missing that the red set has is an x plus 2. So I'm going to have to give that to the top. So let's do that. I'm going to set up my common denominator. So the left one, I'm going to have to FOIL. So first times first, x squared. Outer and outer, 3x. Inner and inner, 1x. And then last and last, 1 times 3. And then the other one, I just have to distribute 2 times x, 2 times 2. The whole reason why I did that now is so that I can write this as one fraction. So I just have an x squared. 3x plus 1x is 4x, plus the other 2x is 6x, and then 3 plus 4 is 7. Technically we're done, but the last thing I'd like you to check for is to see if we can cancel anything. So let's go ahead and factor this top. I want to multiply to 7 and add to 6. What two numbers do that? Well, nothing does that, right? Because the only things that multiply to 7 are 7 and 1, but there's no way I'm going to add those to also get a positive 6. So it turns out this is the answer. If I asked you for what are the values that are restricted, well, from this first guy, we wouldn't want negative 1. From the next one, I wouldn't want a negative 2 because that would make it 0. And the last one, I wouldn't want a 1. All right, the final two examples are the real, we call them humdingers in my class, but they look a lot worse than what they are. So this is kind of combining everything together in the unit. This is called a complex rational expression. It's complex because it's like fractions inside of a fraction. But we're going to take it in pieces. Let's look at just the top first. So ignore everything outside of that. First off, this 1, I could write it over 1. 1 over 1 is the same as 1. So let's get a common denominator up top. Well, this one has a 1 and this one has an x. So really, we just need to give the left one an x. So then I'd have to give the top an x. So if I do that, hopefully you agree that it would look like this. Which then, since they have the same denominator, I could just say x plus 1. There's the top. Now let's focus on the bottom. Technically this one is over 1. And it would also need a common denominator. This one has a 1, the right one has an x, so I'm going to give it an x. So I would get x over x minus 1 over x. So x minus 1 over x. And now both of them are still being divided, so I still have a mess. But I'll tell you, once you have it down to one fraction up top and one fraction in the bottom, there's one step left. And it's what we talked about when we did the dividing problems earlier. We multiply by the reciprocal of the second expression. So I'm going to take my blue, and instead of dividing, I'm going to multiply by the reciprocal of the red one. I flip-flop it. And now the easy part, I see, can I cancel anything? Yes, I can cancel the x's because there was multiplication, but that's it. So my answer would be x plus 1 over x minus 1. Okay, one more. Again, let's focus just on the top first. So I'm going to do a common denominator so I can write it as one fraction. So the left one, it looks like, would need a 2, and the right one would need an x. So I'd get 2 over 2x minus 3x over 2x, which, if I wrote that as one fraction, 2 minus 3x over 2x. Now let's look at the bottom one. common denominator, I would need a 4. In the right one, I would need an x. So we would get 4 over 4x plus 3x over 4x. Write them as one fraction now. 4 plus 3x over 4x. And now the whole reason why we did that, once we have one fraction over one fraction, I'm going to take my blue guy and instead of dividing, I'm going to times by the reciprocal of the second. And now we just see, can we cancel anything? I can cancel the set of x's, and 4 divided by 2, I can cancel a 2 out of both. So I'd still have a 2 left up top. So this answer you could write one of two ways. You could say 2 and then the 2 minus 3x. I would accept that as an answer. Or you could actually distribute the 2 in and say this. Either one would be acceptable. So there it is. This is the completion of Unit 1. Like I said, everything in this unit we will be using at some point or another throughout the rest of the class.